Hello and welcome to today's webinar presented by Dlubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's presentation is the ASCE 7 2016 Response Spectrum Analysis in RFEM 6. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and also a technical support and sales engineer, and I'm located in Philadelphia, Pennsylvania. My colleagues Alex Bacon and Siska Choa will be your moderator, answering any questions you may have. They are both technical support engineers, also located in our Philadelphia office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within this same dialog box. If by chance we don't get to all your questions, we'll certainly send you a follow-up email afterwards. So regarding the content over the next hour today, we will begin with a modal analysis of our structure shown over here on the right to determine the natural frequencies and mode shapes. We'll then move on to a response spectrum analysis, and this will be specific to the ASCE 7 2016 standard. For both the modal analysis and response spectrum analysis, we will review the results both in tabular format as well as graphical format within the main program RFEM. We also have added a new add-on within RFEM 6 called the building model. So we'll take a look at this today and how it offers us to organize our result data from the response spectrum analysis according to the various stories. And finally, we'll take a look at considerations of topics like base shear, story drift, and P delta, and how we can consider that within the response spectrum itself. So we'll begin with our example within RFEM 6 today. And you can see that I've taken the time to already model this multi-story structure for the sake of time. And if we're interested to view what the input data is for this particular structure, we can take a look at our navigator over on the left. We see that all of the materials are defined with the 4,000 PSI concrete. As far as my columns, I have defined these as square 12-inch by 12-inch, 4,000 PSI sections. And finally, we have our thicknesses shown here. So we can see that our floor slabs are defined with 12-inch thickness, as well as our shear walls throughout each one of these levels is defined with 8-inch thickness. Both of these are also the 4,000 PSI concrete. I have also taken into consideration the loads on the structure. So if I use my drop down at the top, we can see the various load cases that are defined. And we begin with self-weight. So this will automatically be considered underneath the hood within the program. No additional loads are applied for this particular load case. We can take a look at our dead load, and we see here that we have surface loads applied at each of the levels. We also have a live load, which very similarly has a surface load applied at each of the floors. We have a separate roof live load shown up here at the top. And finally, we have our snow load. So all of these load cases will come into play with mass conversions when we're talking about our modal analysis. So to begin that modal analysis, we need to activate this particular add-on. So within the main program, if we right-click on the model name within the navigator, we can visit our base data. And under the second tab here are all the various add-ons that maybe we purchased for our particular RFEM 6 license, and we'll be activating the modal analysis here under dynamic analysis to begin. Now, under the third tab, we will generate our load cases and combinations automatically according to the ASCE 7. And under the Standards 2 tab, if we look down here at the bottom, this is where we will set the relevant standard for dynamic analysis. So you can see within this dropdown, we have the ASCE 7, we also have the NBC standards, and many other international standards. And over on the right, we would select which edition we prefer to run. Today we'll be running the 2016. Now, a modal analysis is code independent, but what we will be referring to the ASCE 7 is particular topics such as our mass combination, which we'll see a little bit later on. So once we have enabled this add-on, we will revisit our load cases within our load cases and combinations dialog box. So here is that self-weight load case listed. And we can see the analysis type is set to a static analysis, but because we have enabled the add-on, we now have the additional option here to run a modal analysis. And you can see that the settings will be modified here depending on this analysis type. So within the modal analysis settings, let's take a look at what we can adjust. There are a couple default options shown here, so you can either create a new type of setting or modify one of these default options. The first dropdown will indicate the method for determining the number of modes. So we can see that the default is set to user defined, where I can input directly the number of modes to solve for. Alternatively, we have this automatic option to reach the maximum natural frequency. And as a user, you would input in that natural frequency and the program would calculate the number of modes in order to reach this value. So for this first example, we will use the user defined with 4 modes. Then we have the method for solving the eigenvalue calculation. The default here is the Lenko solver. So this is an iterative method to determine the lowest eigenvalues and corresponding mode shapes. This really will allow for a quick convergence. The second option is the root of the characteristic polynomial. So this is more of an analytical solution that's solved using a direct method. So this might be a little bit more ideal for small structures for the precise calculation of higher eigenvalues. And finally, we have the subspace iteration. This is going to be ideal for large FE models where only a few eigenvalues are determined in one step. So we'll leave this as a Lenko solver. Now we do have this option to turn on modes beyond a set frequency. So this will eliminate any local modes where maybe members and surfaces have a very low natural frequency. And finally, we have over on the right our mass matrix settings. So within this dropdown, we can see the first type is the diagonal mass matrix. Essentially, masses are going to be lumped at every FE node. Alternatively, we have the consistent mass matrix, and this is going to use shape functions instead for a more realistic mass distribution rather than necessarily lumping those at every FE node compared to the diagonal option. And finally, we have the unit mass matrix. This is where the mass at every FE point is set to a magnitude of 1.0. This is certainly a more mathematical approach. It's really only used for numerical analyses. So we'll stick with the diagonal mass matrix for this particular example. Now we have the settings tab here, and under the mass conversion type, we have 3 options. The first is the Z components of loads. This just means that any of those load cases that we previously defined will be converted to mass in the vertical direction only. So if we have loads defined in the upward or downward global Z direction, they will be converted. The second option is the Z components of load in the direction of gravity. This just means that only downward loads will be converted to mass. And finally, we have the full loads as mass. This means that if we have any loads defined in any of the degrees of freedom or any direction, X, Y, or Z, those will automatically be converted to mass. Over on the right-hand side, we have the option to neglect masses. The current default option is no neglection. We'll get back into this option in just a minute. And finally, we have the minimum axial strain to set here for cables and membranes. So we can define that initial strain here. We don't have any cables or membranes for our structure today, so we'll leave this alone. So once we are done defining these settings, we click OK and notice that we're importing the masses only from this initial self-weight load case with the self-weight activated over here on the right. So what I can do is to click calculate. The program will generate the FE mesh, and then it will run through this modal analysis to determine those 4 different eigenmodes. So once the calculation is complete, you can see here in our navigator, we now have a new tab for our results. And within this dropdown are 4 different eigenmodes with the natural frequency given directly to us. So we can kind of cycle through these to see the response of the structure for those 4 different eigenmodes, again, based only on the self-weight mass conversion. The mode shape is given here within these options over on the right. If we scroll down to the very bottom here of the navigator, we can see that the scaling and mode shapes is set with these options. Now, currently it's set so that the highest value is equal to 1.0, which we can turn on our navigator here and see the color panels is associated here with the scaling of that mode shape set to a value of 1.0 for the highest. Now, the graphical options are great, but the table format is also really important for interpreting our results. So you can see within my table options down at the bottom, I do have the modal analysis selected here, and I have 4 different tabs. So beginning with this first tab, this is going to show me, again, my 4 different eigenmodes, and it's going to display the angular frequency, the natural frequency, and the natural period of our structure. The second tab is very important because this is showing us our mass participation. So we see here the mass participation in the translational X, Y, and Z directions, as well as the rotational about the X, Y, and Z directions. And down at the bottom line is showing us our overall mass participation percentage. So if we refer to the ASCE 7, and in particular section 12.911, there is the requirement to meet that 90% mass participation in these X and Y directions. So currently we only have 70% in the X and 68% in the Y. So we'd probably want to take care to maybe consider additional masses beyond the self-weight, solve from some additional eigenmodes so that we do reach that 90%, which we'll move forward with in just a minute. We also can see under this last tab the masses at every FE mesh point. So you can see that as I scroll through this table, it's pointing me to the location with the red arrow here, exactly where the FE mesh point is located, but as well as the masses that are being converted for this modal analysis. And the table format is nice. We can export this to Microsoft Excel, but new within RFEM 6 is the graphical representation of the masses as well. So we see this over on the left within the navigator where we can activate the masses. Now it looks a little overwhelming, but if we zoom in, and I will create a user-defined visibility here for only my top story, and I will also convert this to a wireframe view. If we zoom in, what is occurring is it's showing us the mass at every FE mesh point. You can see this symbol is a magnitude of how big the mass actually is. So we can see the mass distribution along the lengths of our columns, as well, again, as every FE mesh point for this top surface. Well, if you remember, under the settings here within my modal analysis, we did have the option to neglect masses. So we currently did not do any neglection, but we do have the ability here to neglect masses for nodal or line supports, but we also have this user-defined option. So when we choose this option, we get an additional tab. And under this initial dropdown, I can select here any type of object, such as a surface. Then I can graphically select my surface or surfaces that I'd like to neglect the masses. So we'll select this top floor, surface number 53. So when I click OK, the program tells me that it needs to clear out the results, and that's okay. So now the masses should be completely neglected at every FE mesh point for this particular surface on top. Keep in mind too, we have the ability to manually apply masses to our structure as well. And we do so with these options up here in our toolbar, such as a nodal load, line load, surface, and member load. So if I launch a new nodal load, the difference here is that the load type is not set to a force, but rather we can choose the option mass. So we would give it some magnitude. So we'll set this to 2,000 pounds. And then I can graphically select the nodes that I'd like to apply this to. So we'll select node number 409 in the upper left corner. I click OK, and I should see the graphical representation here of this manually applied mass. So if I rerun this calculation then for that load case 1 for self-weight, which still includes my modal analysis, we should see slightly different results here. So we'll still have the 4 different eigenmodes within the available dropdown, but notice as I'm displaying my masses and I zoom in here, sure enough, at every FE mesh point, the mass is set to 0 because we have neglected that under those settings. But if I turn off the display of my loads here, I will see that 2,000 pound mass that I have manually applied in the upper left corner. So we'll go ahead and delete this applied mass. And what I'd like to move on to now is to run the modal analysis for the entire structure, but let us consider the additional load cases now for the mass conversion. So what we'll do here is to go up to the load cases and combinations, and I want to change the analysis type back to static analysis, and we'll change our action category here for self-weight back to dead load. And instead, I'm going to create a new load case, and we'll give it a load case name here called modal analysis. The analysis type will be set yet again to modal analysis here. Now within my settings, I do want to make some changes here. The first is I want to solve for a total of 10 eigenmodes. So we'll increase that slightly. The mass matrix settings, I'm going to uncheck a few of these degrees of freedom. So notice that we have 6 degrees of freedom here. 3 are taken into consideration for mass in translation and 3 in rotation about those global X, Y, and Z axes. So I will uncheck about the axes X, Y, and Z. I'm also going to uncheck my mass consideration in the vertical Z direction. And the reason for this is we'll run a slightly quicker calculation, but more importantly, we'll be able to reach that 90% requirement set forth by the ASCE 7 and the X and Y directions a little bit more efficiently when we deactivate these masses that we're not concerned about within these degrees of freedom. Now, under the settings, we want to change back the no neglection option here because we do want to consider the mass at that top level. So once I have made all of these modifications, I can click OK. And we should be ready to run our calculation, which we can see we can have the calculate button utilized down here in the lower portion of that dialog box. So this will run through the 10 different eigenmodes now, and you can see that it solves rather quick. Again, making those changes to the mass matrix was also helpful. So within our drop-down box, we now have 10 different eigenmodes shown that we can kind of cycle through again to see the response of the structure. But most importantly, I'm going to refer back to my table results and that effective modal masses option. And I want to view my mass participation. In the X direction, I see it is 95%, and in the Y direction, I see it's 93%. So therefore, we're meeting those requirements, and we can use this modal analysis to now move forward with our response spectrum analysis. Okay, so one other thing that I did want to mention though, actually, let me go back one step. I currently am meeting the 90% with the self-weight alone, but what I'd also like to show you is how to import in a mass combination instead. So currently, again, we're only considering this self-weight, but rather when we refer to the ASCE 7 and in particular section 12.7.2, it does give us some criteria for considering other load cases beyond just this simple dead load. So we can combine topics like live load, snow load, and so on. So notice within this dropdown, we're currently importing in only the self-weight. Well, we need to create what we call that mass combination. So we jump to our design situations here. And if any of you joined me for a previous webinar, we know that these design situations are eventually used for concrete design, steel design, and so on. And they are able to generate the load combinations for us. So we see here the LRFD load combinations for factored load combinations and ASD for unfactored load combinations. I'm going to go ahead and uncheck these for now because they're really not needed for this initial example, but rather I'm going to create a new design situation. And over on the right-hand side here, what we can do is to utilize our drop-down to scroll all the way to the bottom to choose the effective seismic weight. So if we click on our info button here, this comes directly from the ASCE 7. And again, this just tells us how we can combine those different load cases according to section 12.7.2. So it's not enough here just to create the design situation, but if we're more interested in seeing those individual load cases actually generated, we'll jump to our load combinations tab. And here is our mass combination, in particular under the assignment tab. So again, we see those dead loads, live loads, snow loads, and including the roof live load all listed here. Now, there might be the question, well, how do we neglect some of these load cases for our mass combination, or maybe how do we modify the factors out in front? And this is all controlled back under that load cases tab. So we can jump to live load, for example, and under the additional settings, here is the checkbox to completely neglect that from that mass combination. So we can uncheck this and it will be excluded. If we leave this checked, you'll notice we have some additional drop-down options here, again, directly from the ASCE 7 that's going to modify that factor out in front of that particular mass combination. So back under the modal analysis, if we wanted to take into consideration not only just the self-weight, we can now import in that mass combination that considers the dead load, live load, snow load, and roof live load. So we can once again run our calculation just to ensure that we're meeting that 90% mass participation. Of course, we'll have no issue with this, as the self-weight alone would also reach that 90%. And we can see here a little bit better results, 95% in the X and 93% in the Y. So in either scenario, we can now move forward to our response spectrum analysis. So what we'll do here is to go back to that base data. We can right click to access the base data dialog box, and under the add-ons, we're now going to activate here the response spectrum analysis. We'll still be referring to the ASCE 7 for this. So once we click OK, not much has changed here within our model. We'll revisit the load cases and combinations dialog box to yet again create a new load case here. The load case name is going to be response spectrum. And what we want to set the analysis type to here, now that we've enabled this, is a response spectrum analysis. So we have some additional settings here that of course are going to be slightly different from our modal analysis. So we'll take a look at the initial settings for the spectral analysis, which we can access those with the button here. We have several options here. The first is the combination rule for our periodic responses. And if we take a look at this dropdown, we have the SRSS, we have the CQC, and absolute sum, as well as some additional settings. Now we also have the combination of directional components. And if we take a look at this dropdown, we also have the SRSS, but a couple of different options such as the scaled sum and absolute sum. So I think for these options, it's best to take a look back at the PowerPoint to explain in a little bit more detail what exactly we're setting here. So with this first option up at the top, the combination rule for the periodic responses, well, this is how we're going to define how those responses from the different eigenvalues and the horizontal directions are combined. So what I mean by this, I'm going to jump ahead to what we'll see with our results eventually with the response spectrum analysis, is that ultimately, remember, we're solving for 10 different eigenmodes for our particular modal analysis of this structure. When we apply the response spectrum, we are going to get results in both the X and the Y direction for each one of these eigenvalues. So the question is, well, how do we combine all of these to get a single result in the X and a single result in the Y? And the answer is with one of these options available to us here within the dropdown. The first option is the square root sum of the squares, or the SRSS rule. We can see that the equation is listed here. It's essentially going to combine the max results. We square the results, we add them together, and we take the square root. Now, inevitably, when we take the square root, the signage will be lost. We also have the complete quadratic combination, or the CQC rule. So with this option, you can see we sum these together as well. We take the square root, but a significant difference here between the SRSS and CQC is that we are now taking into consideration the correlation coefficient epsilon. And epsilon, the equation is listed here, will now consider those damping factors for our structure. So SRSS, we don't have that ability. And finally, we have the absolute sum, which is the third option within the dropdown. This is where the modal analysis is conservatively superimposed. So we're simply adding them all together. So definitely the most conservative out of the three options available to us. So once we have selected one of these combination rules, what we'll see in our results then is a single value for the results in the X and a single result for the periodic mode shapes in the Y direction. Now, there is an additional checkbox below this called the Use Equivalent Linear Combination. Well, with standard SRSS or CQC combinations, the problem is that corresponding internal forces are lost. And what I mean by this is if we look at the max axial force, we'll actually lose the corresponding moment, for example, at that location. So by turning on this checkbox, we'll take advantage of the equivalent linear combinations instead to give us a more realistic result as well as the correct signage. So if we look at the SRSS linear combination, we can see the difference here of the equation versus the slide before, as well as the CQC linear combination, again, taken into consideration that damping factor though. I'll explain the other two options while we're still within this slide. The signed results using the dominant mode. So the dominant modes are going to be those that have the most mass participation. And inevitably, again, when we take those square roots, we lose the signage. So with those single results in the X and Y direction, we do have the ability here to assign back the signage from the dominant modes if we turn on this checkbox. And the final option, the save results of all selected modes. If you saw in the previous slide, I was showing you how we have an X and Y result for each one of those eigenvalues. This will just export out to RFEM so we can view the results for each one of those X and Y directions for each eigenvalue. Now we also have at the bottom of that dialog box the combination rule for the directional components and a few options here within our dropdown. Well, once we have determined from the previous slides a single result in the X and a single result in the Y, there are some requirements in many of the standards, including the ASCE 7, how we will further combine these for the actual structural design. And our first option here is the SRSS rule. So this is similar to what we saw on the previous slides. We square them, add them together, take the square root. Now, the more common option is probably going to be the scaled sum or the 130 rule. And if we refer to the ASCE 7 section 12531A, the code tells us that we should apply 100% in the X and 30% in the Y and vice versa. And then finally, we have the absolute sum. Again, a very conservative approach here. We're just simply going to take 100% of the X and add it to 100% of the Y. So assuming that we choose something like the 130 rule with the scaled sum, what we would see in our results then is the two result options here, 100% in the X direction and 30% in the Y, and vice versa, 30% in the X and 100% in the Y direction. Okay, so we'll go back to the settings here to explain this a little bit further. The settings we'll use today is the SRSS, but notice that over on the right, damping is grayed out. That's only activated when we choose the CQC rule. Then we can choose that damping ratio either constant for each mode or separately for each mode. So utilizing the SRSS, maybe we want to turn on that equivalent linear combination as well as the option to save the results of all selected modes. The combination of directional components, we can see here that we'll use the 130 rule directly from the ASCE 7. Now there is an additional checkbox here to consider the independent directions in the envelope results. And what this is going to do is eventually we'll get an envelope solution of those 230 results. And the program will tell us what is the worst case scenario, including both the max and min for our internal forces, deflections, and so on. When this option is checked on here, we will also consider 100% of the X, as well as 100% of the Y in our envelope solution. If we turn this off, then we won't consider those independent orthogonal directions in the envelope solution. Okay, so once we are done with these settings, we can click OK. And you'll notice here down at the bottom, just to quickly mention this, there is also accidental torsion. We can turn this on. This relates to section 12842 within the standard. And the code tells us that when diaphragms are not flexible, we need to consider an assumed displacement of the center of mass from the actual displacement. And here is where we'd apply 5% of the structure's dimensions perpendicular to the applied forces. So you can see 5% is already set by default, as well as the program automatically detects the building length in both the X and the Y directions here. But if we want to make changes to that, we can use this checkbox option here to override those lengths. So therefore that accidental torsion will be considered. We won't be considering that for today, so we'll leave those off. Now, the import modal analysis from the load case. If we use this dropdown, we only have a single modal analysis solved for, but maybe we created multiple modal analysis. For example, if we wanted to create different mass combinations and kind of play around with those, we might have multiple options available to us here. The action category. Today's example is primarily concerned with the horizontal earthquake forces. So therefore, I set that action category relative here to only horizontal forces. But if we wanted to create a second response spectrum here for vertical, so maybe we want to keep those two separate, then we would want to modify that action category here as well. The second tab is the response spectrum itself. So we need to tell the program we'd like to apply the response spectrum in the horizontal X and Y directions. I won't be activating the vertical here, but again, maybe we create a second response spectrum where we activate Z alone. So here within the response spectrum settings, I can take a look at this dialog box. And within this dropdown, we're directly referring to the ASCE 7. Remember, we set that under the base data. Therefore, the response spectrum diagram that we're seeing down here at the bottom is entirely referring to that standard. But we have a couple different options here. Perhaps we want to choose user defined, where we can input in table format directly the response spectrum diagram. Alternatively, we have the option here for an accelerogram. And if we create a new accelerogram definition, we can also take advantage of our library. And within the RFEM library here, if we activate it, we have over 2,490 recorded accelegrams for all of the various countries, including Canada, as well as the United States. So we can take a look at all of these recordings here. We can import them in to be applied for our response spectrum as well. So I'll cancel out of these because today we do want to run this according to the ASCE 7. Now let's take a look at the various settings here that are available to us. So the first is the spectrum direction, and we use this dropdown. We have both horizontal and vertical. This refers directly to chapter 11. There are a couple different workflows depending on if we're running a horizontal response spectrum versus vertical. So we would want to define that here. The modal response parameters. So we use this dropdown and we see there are three options. The first is no modification, pretty self-explanatory. We're not going to make any modifications to the response spectrum. But if we choose force related, this comes directly from section 12.912, that the response spectrum should be divided by R over I sub E. So when we choose this option, we see we have a few new variables here, including the seismic importance factor I sub E, and I scroll to the bottom, I also have the response modification factor R. Now, alternatively, if I choose the displacement related, again from the same section, I'll take my response spectrum and I'll multiply by the variables C sub D over I sub E. I sub E is still listed here. We scroll to the bottom. That is now modified to the deflection amplification factor. We'll leave this as the no modification for today. Now, the third drop down here is the spectrum type. We have design. We also have the MCE sub R. So design is just going to be no modifications. We'll refer to section 11.4.6 within the code. But the MCE sub R is the risk targeted maximum considered earthquake. And what we'll do here is to take that design spectrum and multiply by a factor of 1.5. So we'll leave this as design for today. So there are some other variables here that as the user you would need to input in specific to your project, such as the site class. Maybe we modify this to site class C. Now for all of these variables, they do come directly from the ASCE 7. For those of you who are not familiar, on our website at dlubal.com, if you go to the solutions option and hover over it, under the online services, we do have these snow, wind, and seismic load maps. And what we have done with this particular GeoZone tool is we have integrated all of these various standards, including the ASCE 7, the NBC, as well as many other international standards with Google Maps technology. So what you can do is to simply type in the location of your project or the address, and then when we have the seismic option selected up here at the top, all of our various variables to take into consideration with the response spectrum are available to us here. So just a little bit more user-friendly and time efficient rather than having to flip through those maps within the ASCE 7 directly. So once we have all of our variables, we would input them in here, and we'll just go ahead with the default options for today. So I'll click OK now that we have defined our response spectrum diagram here in the X and Y direction, and we have our final tab here, the selection of modes. Now notice here are my 10 different eigenmodes from load case 6, which we previously solved for. And every single one of them is currently checked to be considered for the response spectrum analysis. But we have a nice feature down here at the bottom where we can actually deselect modes that are not meeting a set mass participation. So maybe I set this to something like 3%. So notice I now have some eigenmodes that are now not selected. They will not be considered with this particular analysis. But yet, if we look over here on the right, we're still meeting the 90% mass participation. We have 93% in the X direction and 92% in the Y direction. So this will just speed up our calculation a little bit. It will eliminate some of these results that really aren't so important for those eigenmodes that don't contribute significantly to the mass participation. Okay, so now that we have covered all of the various settings within this response spectrum, we are now ready to run our analysis. So what I'll do is to just click the calculate button here as well. And the program has already solved for that modal analysis, and now you can see we're applying the response spectrum analysis. It solves within seconds. This is something new within RFEM 6 that will take advantage of that multi-core processor within your computer. So what maybe would have taken a couple minutes back in RFEM 5 will solve within seconds within RFEM 6. So a pretty big advantage there. So we can take a look at here our dropdown for the spectral analysis envelope solution. So remember I talked about the results will create this envelope solution to give us the max and min results for deflections, internal forces for our members, and so on. And the scaled sum envelopes is going to include the 130 rule and also the independent X and Y directions of what we're viewing here graphically. Now I can always switch to any one of these different options to see the results and how the structure is responding to that particular response spectrum. Now remember, we also exported out the results for all of the independent eigenvalues here in the X and Y direction. So we're now viewing the global deformations here for that envelope solution on our structure. But we also have the ability to view the internal forces for our members, for example. So I can scroll in here to maybe only our top floor. I'll convert this to a wireframe view, and currently we're viewing the normal or axial forces within those columns. But we can also view the shear forces in the local Y or the local Z direction, maybe bending moments. Same concept for our surfaces here. So we can view the internal forces of these concrete slabs such as MX, MY, and so on. So this is also a pretty significant difference here between RFEM 5 and RFEM 6. So previously in RFEM 5, we would export out those equivalent loads back to the base program, and we would need to rerun the calculation to determine what the internal forces are. Well, in RFEM 6, you'll notice that we immediately get the internal forces at every FE mesh point. So no longer are we exporting out equivalent loads, but we're directly determining what the values are in order to give us information like deformations, our member internal forces, and surface internal forces. Okay, so We also have our table format, of course, for the spectral analysis. So here's our modal analysis that we already covered, but we also have the spectral analysis available to us. And within our second drop-down box, we can view the results by member, for example, such as the internal forces. And as we scroll through this table, that red arrow is going to show us exactly where we are within the structure. So the other option here is to view the results by the surface. Now, I'd like to move on to the introduction of this new add-on, the building model, because previously in RFEM 5, when we wanted information like our base shear or maybe topics like drift, it did require some manual work, such as creating a result beam, and we kind of had to export out those results into maybe Microsoft Excel in order to get information about story shear. So what we'll do now, and I'll convert this here to a rendered view, let us take a look at, let's turn off our global deformations. We will revisit under our navigator, our base data, and under the second tab, we will now activate the building model add-on. So when I click OK, at first glance, it kind of seems like not much has happened with our results here. The only thing that's now available to us here within the navigator is a new tree option for the building model. And we see here building stories. So this gives us the ability to right click to create a new building story. So previously in RFEM 5, and similarly still in RFEM 6, this is a general FEA program, but now we have the ability to actually define these different stories or these different floors that we previously didn't have. And this add-on is actually quite intuitive. The only thing that we need to do now for this initial floor is to define the bottom elevation at 0. And the top elevation is going to be at 13 feet. So take a look at this. Our data will update over on the right-hand side. Now, there are some additional settings down here at the bottom. And most importantly, notice the default option is that the story slab stiffness is set to a rigid diaphragm. So we'll actually apply that rigid diaphragm to that particular floor. Now, we're working on expanding these options to include different diaphragm types in the future. Previously, again, we didn't have the concept of diaphragms so much within the older version. But remember in our model today, I actually have modeled these surfaces at each level with true concrete surfaces, 4,000 PSI concrete. So the true stiffness is being considered more like a semi-rigid diaphragm. So instead of applying a rigid diaphragm over that, we'll just clear out that entry. Then it's really as easy as just selecting a new building floor definition all the way up to floor 96 with a top elevation of 91 feet. So the program by default will apply that same 13-foot distance for the height of each floor. But of course, if you have varying heights, you can go in and adjust them as you see fit. So that's really all that we need to do here within this particular add-on. So when I click OK, what you'll notice is that I get a different symbol shown here outside of the structure. And this is just defining the various stories and the lower and upper elevations respectively. Now, my results are still here from my response spectrum. I can take a look here at this tab that we were just in. I'm also looking at the spectral analysis results in table format, but notice now that we have activated this add-on, we get a new option. So rather than viewing the results by members or surfaces, we now have the results by stories. And we have 4 different tabs here. And now within the story actions, we're going to give you a summation of the shear forces at each level. So we can scroll through to see the max and min story forces here for shear in the X direction, as well as the Y direction. Now, similarly, under the second tab, we have here the inner story drifts. So we're going to give you the inner story drift at each one of these levels as well. Now, this is all based on the center of mass at each one of these locations. The third tab is going to provide the center of mass location coordinate points. So we can see here an X and an Y that's given. Now, if we did define those rigid diaphragms at each level, we'd also be given the center of rigidity at these locations as well. But because we're using the true stiffness here, only center of mass will be provided. And finally, this fourth tab, the forces in the shear walls. So this actually will tie these shear walls to each level. And notice that when I zoom in here, I'm kind of scrolling through this different table, and the program will highlight exactly which shear wall I'm looking at. We have summed up the total forces for that particular surface element. So I'm seeing a summation here of my axial forces, as well as my bending moments, and of course the shear forces. So we might be wondering, well, how is all of this automatically done? We have a new feature over here on the left under the navigator for the results sections. And if I expand this, we can see every single shear wall listed here. And I can double click on any one of these. And we create automatically what's called a results section. And this results section will match the geometry, of course, of the surface element itself, and it will sum up those forces over the entire length and height. So this is pretty powerful in the sense that we can export this information to Microsoft Excel. Perhaps we just want to do some further design with our own in-house tools. That's possible now without having to do any manual work to sum up those forces. So we're pretty proud of this building model add-on and just a lot of improvements that we made for the result output, especially in relation to the response spectrum analysis. Now, the question might be, well, what do we do further with topics like the base shear, maybe drift? And we will refer back to the PowerPoint here and specifically to the ASCE 7 to discuss this a bit further. The first will be the topics of base shear and drift, and in particular looking at section 12.9.141, the scaling of forces. So with our example today, we are taking into consideration this shear force, and we'll be looking at the base shear in two orthogonal horizontal directions, X and Y. Well, we get this information new from RFEM with that building model add-on, and it's just simply the base shear from the combined responses. If you remember the previous slides, according to the SRSS, CQC, or absolute sum. And relating this back to the standard, this would be the variable V sub t. Well, then we need to look back at section 12.8 within the standard, and we need to calculate the equivalent lateral force procedure base shear. Now, the equivalent lateral force procedure we do not have implemented within RFEM. Rather, we're taking the response spectrum approach. So this would be some manual calculation to determine what that base shear is from this section 12.8. Now, when our RFEM base shear, again in the X and Y directions, is less than 100% of V calculated from the equivalent lateral force procedure, then we do need to scale our forces up by a factor of V over V sub t. Now, similarly, there are requirements for the scaling of drifts in section 12.9.142. So when V sub t, again, that's that RFEM base shear we get from the building model add-on, is less than C sub W times C sub S times W, which is the seismic response coefficient multiplied by the effective seismic weight. In other words, this is V from the equivalent lateral force procedure. Same topic here. But if that is less than V, then we need to scale the drifts by a factor of V over V sub t. So same concept here for our base shear as well as our drifts. So the question might be, well, how do we take into consideration these factors within the RFEM analysis? And you can do so directly with our scale factor. So we've already been in this dialog box where we were defining our response spectrum definition, but I'll show you in just a minute again where we can find that scale factor to make those modifications. In a very similar manner, when we're talking about P delta, P delta is discussed in section 12.8.7, and in particular, if we look at equation 12.8-16 to calculate the stability coefficient theta. Well, P delta can be neglected when this theta value is less than or equal to 1.0. So P delta would not need to be considered with the RFEM model at all. However, if theta is greater than 0.1 but less than theta max, and theta max is an additional equation within the standard in this section, then we do need to multiply both the displacements and the forces by 1 over 1 minus theta. The code goes on to tell us that if theta is greater than theta max, then we do need to completely redesign this structure because it may be unstable. So if we find ourselves falling in between this range here, between 0.1 and theta max, and we want to apply this additional multiplication factor, again, same concept, we will go ahead and apply that in the scale factor and the response spectrum definition directly. So going back to RFEM then, I'll just quickly point out where that is exactly. If we go here to our response spectrum load case, and under the second tab, the response spectrum, we see here the scale factor where we can apply those modifications. Okay, so the final topic now is that we've run this complete response spectrum, but the question is, we have the results from the earthquake forces. How do we combine these with the additional load cases, such as live load, snow load, in order to do the structure design? Well, yet again, I will go back to our model here, and let me just get a better view. We'll cancel out this visibility. We'll go ahead and turn off the results here and kind of zoom out. So I'm going to revisit that base data under the model name for the last time. And we're going to activate here under the add-ons, the concrete design add-on. So I've given previous webinars on concrete design, steel design, timber design. So clearly we don't have time for that today. So you can pick up at the end of this webinar and view one of those additional webinars to move forward. But if we wanted to do the concrete design according to the ACI, which would be set under the second tab, I want to show you how we can create these design situations now that can be taken into consideration. So when I click OK, we will go back to our load cases and combinations, and back under the base data, we see the option here under this base tab to activate the result combinations. And with this, we're also activating the subresults, and I get a new tab over here called result combinations. Well, going to the design situations, remember we deactivated these factored load combinations and unfactored load combinations. These can be applied for our concrete design. The problem here is that these load combinations will not be able to combine the results from our response spectrum analysis. Those earthquake forces will just simply be neglected. So what we want to do here is to create a new design situation type. And I'm going to use my drop-down box to select this load combination number 6. So this is, again, directly from the ASCE 7, section 2.3, my factored load combination number 6. And I can even take a look at my info button here to see exactly how my earthquake forces are combined in this particular load combination with the additional load cases. Well, instead of creating load combinations from this particular design situations, I'm going to use my drop-down box to create a result combination. And it's exactly as it sounds, that we're going to combine results now rather than combining loads. So we're going to take the results from the additional load cases like dead load, live load, snow load, and we're going to add them to the results of our response spectrum. Now, this obviously has to be done with a linear analysis. You can't superimpose second order effects and the results with each other. So everything is done linearly under this result combination. But before we revisit this here, I'm going to make a copy of this particular load combination and just slightly modify this to my factored load combination here, number 7. I click on my info button, I can see here it's just a slightly different requirement from the ASCE 7 load combinations, still considering those earthquake forces. So I jump to my result combinations tab and I see them listed out in more detail. And in particular, I can view my assignment and I can see dead load, live load, snow load, as well as now my earthquake forces all under this single result combination. Now we activated the sub results. So currently the scale set envelope, which we've already talked about, is going to be that envelope solution considering the 130 rule as well as the X and Y directions. But if I'd like to have a little bit more control over that, not necessarily use the envelope solution, I can use this drop down box now to maybe select 100% in the X, 30% in the Y, or vice versa within this particular result combination. Same concept then for my second load combination or second result combination that I created here. I only am considering the dead load case as well as the results from my response spectrum. So now back under the design situations, you can see that we can utilize these for the concrete design directly. Okay, so we will jump back to the PowerPoint here to close out our presentation today. I do want to talk just quickly about future RFEM 6 dynamic developments. So currently we're working on adding the ASCE 7 2022 standard within RFEM 6. So that was recently released. So hopefully that will be available within the coming months. Same topic for the NBC 2020 that was recently released. We currently have the NBC 2015 and some older versions available in RFEM 6, but we want to stay up to date with those. So that will be coming up. We're currently working on pushover analysis as well. We somewhat had this in RFEM 5, but it required maybe some manual work. So with RFEM 6, we'll definitely see some major improvements with pushover. And finally, as many of you know, the upgrade from RFEM 5 to RFEM 6 was released in phases. And so essentially, we don't have all of our dynamic capabilities from RFEM 5 yet included, and in particular, time history analysis. So we are working hard with that to release linear time history analysis later on this year. And then eventually, we'll also be working on nonlinear time history analysis. So this is just a brief overview of the topics that we're currently working on that you can expect within the coming months and later this year. So this presentation will be recorded and placed on the webpage that you registered for this GoToWebinar. I also have placed there the model that you can download, and feel free to download the 90-day trial version of RFEM 6, which will include all of the add-ons that you saw today. You can open up this model and kind of follow along at your own pace. If you have any questions about today's presentation or any of our products, feel free to contact us at our Philadelphia office at 267-702-2815, and you can see our email is also listed here at info-us@dlubal.com. So we will have many more upcoming webinars as we continue to introduce the new features of RFEM 6. You can register at dlubal.com under support and learning webinars. As most of you know, I tend to send out a reminder email about a week before these take place, so feel free to register through the email directly. PDH certificates will automatically be emailed to all participants who were here for the full presentation. So that is a requirement from the states that we are pre-approved providers, that if we give PDH, the attendees must be there for the full duration of the presentation. If you yourself did not register for this GoToWebinar, but yet you watched with a colleague or maybe in a conference room type setting and you are wanting PDH because you were here for the full duration, go ahead and request that at the email address, again shown here, that info-us@dlubal.com. So if you yourself did not register for the presentation and you're wanting PDH, just please send us an email, let us know who you watched it with, and we'll be able to add you to that list. Now, PDH certificates are not automatically sent out right after this presentation ends. Probably tomorrow at the latest, Monday, you should see those. And with that said, I want to thank everyone for attending. And as always, we hope to see you at the next presentation. Thank you.